Good morning. I'm Chuck Lever. This is Shirley Ma, my colleague. We're going to talk actually specifically about the Linux implementation of NFS over RDMA. The agenda is slightly deceptive. I just wanted to make that clear. So as I'm going through the slides, if you could just sort of keep these three bullets in mind. These are the overriding sort of takeaways of the talk this morning. We definitely don't want to dive into this work all by ourselves, and it's meant to be an open dialogue. So everything you see on the slides is kind of provisional, and please come see either of us during the rest of the conference if you want to discuss any of the issues that we bring up this morning. So we usually have to make a case for NFS over RDMA and the case has to be against NFS over IP over IB. Whenever we talk to folks, for example, inside Oracle or around, they say, well, why not just use IP over IB? It works well enough. So I'm going to talk a little bit to that comparison because I think that's a question that usually comes up when one advocates for NFS over RDMA. What we found is that there are definite performance advantages, which Shirley's going to get into in a few minutes. And the fact is that if you were paying attention yesterday, I'm sure most of you were, there are some very interesting slides about how the storage is advancing. I don't think larger cache size was mentioned, but on storage servers, the caches are getting bigger. They're like up to multiple terabytes of dynamic RAM in storage servers. That will go very fast, and that's something that's appropriate to get the transport out of the way and make sure that that data is transferred from server to client very quickly. And of course, as we all know, non-volatile is coming very soon, and that's something that's very effective at improving the performance of storage servers. So we think that NFS over RDMA is a good strategy. It gets a lot of software out of the stack and makes the storage go a lot faster. So we wanted to look at Linux because Oracle has a Linux distribution, and we kind of were thinking it might be interesting to enable NFS over RDMA in our storage because we've got a lot of InfiniBand in our products. So we started looking at known implementations. Would this be useful? Could we, if we enabled, say, the client in Linux, could we use it with something? Well, Oracle has an actively supported NFS over RDMA implementation, Oracle Solaris. It's also supported in their ZFS storage appliance, so that would be a good server. It's worth pointing out, though, that the Linux upstream NFS over RDMA implementation has not been supported recently. It's unmaintained, basically. It's been so since about 2008. Current enterprise distributions, Linux distributions, their kernels generally date from that era, so their NFS over RDMA implementation is okay, it works. But upstream, we know that the client is broken. There are bugs, there are crashes. We know the server side is even worse. There are known panics. For example, right now you can't even write to it without it panicking the server. While we've been sort of socializing these issues, we've discovered a couple of other known implementations. ClusterFS is a file system, a cluster file system that Red Hat has marketed. That actually has an NFS v3 only NFS over RDMA implementation, which I just found out last week. And the NFS Ganesha user space server also has RDMA in it, but it doesn't support NFS. They use it for their 9P file system backbone in the server. Are there any others? Did I not mention? Okay, that's what I thought. No, I wasn't trying to be glib, but I would really like to know because in the NFS world, interoperation is absolutely key. And so I would like to know what implementations there are so that we can build our test matrix appropriately. So we set out to evaluate the Linux NFS over RDMA client implementation. We figure that's going to play well with our ZFS storage. So we're going to dive into the client side first, and also since that was closer to working state than the Linux NFS server. So this is our test environment. Pretty simple. We've got a lot of ConnectX-2 cards laying around, so that we're not using ConnectX-3 or newer. We're just using what we've got. I've been doing functional testing. Shirley's been doing some performance testing. Basically, we want to really sort of fuzz test the NFS client from the point of view of the upper layer protocol, not from the point of view of RDMA itself, but we want to make sure that NFS is actually working. So this is a kind of set of tests that we've been trying out. It's been working pretty well, but we've been sticking close to FRMR, the default memory registration mode. We discovered that the alternate modes, that would be Mythica, memory windows, are a little challenging to try out unless you have quite a variety of HCAs on hand. So Shirley will talk a little bit about some of the performance issues we found.
Regarding the performance, the goal is trying to compare the NFS over RDMA and with NFS over IP over IP. For the performance, we focus on CPU utilization, as well as bandwidth and latency, from small message size to large message size, as well as the CPU efficiency, per CPU, how much bandwidth you can get. The workload we use is called IO-Zoom. It's a tool who can measure the NFS RPC operation latency, like write latency, read latency, as well as the multi-stream bandwidth and single-stream bandwidth. In order to make to reduce the variations caused the performance issue, actually we're just using a single NUMA mode, so we don't have a cross-memory access during the performance. We're using direct I/O, so we can really measure the performance, not using the caching data to see. We also look at the interrupt load, whether the CPU utilization, how much from the interrupt. The first graph for the performance is the single reader. We measure lots of data, but I only put the reader data here. So it's NFS read. So the single read I/O zoom throughput, if you look at the X, it's called record length. It's like message size you can define from 16K to all the way up to 16384K. So the throughput is a gigabyte per second. The V3 means NFS version 3. The V4 means NFS version 4. You can see the bandwidth for the small record length is between 16K to 1K, all the way up, similar between IP over IP and RDMA for small message size. But if you look at the large message size from 1K to 16384K, the RDMA much better than IP over IP for both NFS V3 and V4. So any questions regarding the performance number here?
Yeah, why does TCP head south?
Yeah, that's the good question. I haven't turned off the profiling. I'm trying to figure out why. But the one observation, the CPU, this looks like the interrupts, the IRQ, when I monitor the proc interrupts, the IRQ is always 99 percentile at some moment. So somehow...
I'd still expect it to be flat if that were the case.
Yeah. That's some work we need to figure out. But from the data output, it's...
Decide why bother.
Yeah. Yeah, because RDMA is up. Keep up. Right?
So are you using double frames there?
It's using the IPOIPC connecting mode. It's actually like 64K, the MTU size. It's pretty big. Yeah. The second graph is regarding the 12 readers. I showed the 12 streams, basically 12 readers simultaneously read. I have 6 CPU, so we can see the performance for the RDMA, even for the small message size, because you have multiple streams, you have the RDMA performance much better, all the way up from 16K to 16,384 KB. So it's pretty encouraging from the performance point of view. The interesting graph as well.
Why do you say better? RDMA is using more CPU than TCP.
Wait for the next graph.
Next graph, sorry. This graph, CPU using CPU utilization, get more, but when we measure the performance, the divided bandwidth is better. So sorry, I thought this is CPU. Throughput. Okay.
Right, I put both graphs.
Yeah. So it's look at here. That's how the throughput looks like. So if you look at the huge gaps between the maximum bandwidth for the 12 readers, for the bandwidth, total bandwidth almost reach 3 GB per second. When I'm using the micro benchmark from the OFS stack for our RDMA bandwidth test is about 3.2 gigabytes. So you can see after 512 KB, the message size is keep dropping for the TCP bandwidth, but for RDMA it's pretty flat.
As if events are falling. Events are falling for RDMA.
It's actually event-driven, but we're thinking about do the better performance improvement later. Right now it's event-driven. So every completion, they notify, create an event, then we start pull. So it's not every packet pulling. It's kind of you receive the packet from completion queue, receive a notification from completion queue. You put in packet until it's empty. Then we enable the notification again, then come back. But that can be improved. That's a good point. So we can improve better. Like IPOIB right now, IPOIB pulling 4 packets per operation. So right now we pull 1 by 1. But how much benefit come from there, we don't know. We need to do more exercise to figure out. So any questions regarding this one?
Have you computed cycles per byte? The standard. Okay.
Yeah, if you look at the CPU utilization, basically because I use 6 CPU, I use the total bandwidth divided by CPU utilization number. I also divide by 6. The reason is the CPU utilization report per system, not per CPU. If you can see, for small message size up to 512 KB, it's similar.
Did you turn off hyperthreading and C-states?
Yeah. So here you can see after the CPU utilization for the RDMA is much better, but not flat. It's similar observation after 16384K is a little bit drop. So we need to figure out why. We're expecting it to be flat. Performance opportunities. Right now we're trying to go through the code path because we saw the first thing we think about the CPU. If we look at the CPU utilization, the interrupt actually kill the performance. So we're using one interrupt vector. This all the way up to 99 percentile for one CPU for interrupts. The rest of the CPU idle still. So we are thinking about whether we can using some mechanism like using multiple vector or whatever, multiple queue pair to see whether we can reduce the contention to make performance better. Right now, the NFS over RDMA, the size support for is 256K. So we're trying to increase that size. That should help the performance as well. Like interrupt mitigation, just the question raised a few minutes ago. Yeah, we're trying to help see whether if we do some to reduce the interrupts, maybe the perform will reduce the CPU utilization, then performance will be better as well. So that's for the analyzing based on the testing result. For long-term goal is a multi-queue pair, as we talked with Tom team. So the queue pair is multiple queue pairs introduce the complexity of the code. Whether it's worth to do it, maybe we can, based on this yesterday and today's discussion, looks like 2 queue pair to 4 queue pair may be the best choice. But we need to do some test, some experimental, and maybe hack the code to see whether it does help or not help.
There are NFS protocol questions to use multiple queue pairs as well.
Right, that's true.
It's not part of the protocol, so.
Yeah. But whether any chance to, for the NFS protocol to, yeah, we need to study that, how to.
Sure. No, it's a good thing.
Mm-hmm.
Give me a question. So theoretically, why do we expect multiple queue pairs to help?
First, the bandwidth could be all the way up to 3.5 gigabytes. Right now, even we're using 12 readers, we can only reach 2.5 gigabytes. The reason is the CPU utilization for the single vector. We're using single vector, right? Single queue pair. It goes to a single CPU that reached 99th percentile already. The second, according to some discussion from yesterday and today, it looks like a 2 queue pair. The second queue pair performance looks better, right? From the research from other people.
Because I was talking to someone, they said that for example, on Mellanox, one thread and one queue pair can actually saturate the link.
Yeah, from the micro benchmark point of view, we also get 3.2 gigabytes, but it's not up to 3.8 gigabytes. I'm not sure when they could able to center that link. That means.
Or in other words, does the open community recommend multiple queue pairs per connection, or?
That's something we need to study.
The reality is, in our experience, from the SMB perspective, in our experience, multiple queue pairs greatly improves the performance. It's partly the NUMA effects that Shirley refers to. It's also, for some unknown internal reason in the NIC, better for the NIC. To have 2 work queues, to have multiple completion queues, it offers more parallelism to the NIC. Many NICs have more than one execution engine on board, and they often affinitize that engine to a QP. So by creating a second QP, you make use of additional cycles. Even if they don't, they seem to get better anyway. It's a parallel question in the firmware of the NIC. So I strongly recommend multiple QPs for NUMA and for parallelism.
Thank you so much.
Usually when you're using multiple QPs, you are also using multiple CQs, which potentially can report to multiple event queues, and multiple event queues generate multiple interrupts and interrupt vectors, and so you can spread the load over the available.
Yeah, that's what we're trying to help. Yeah, that's a great point. It's basically you have multiple interrupts go to different CPU, you can split the workload. Right now, that workload is limited by a single interrupt. And also the implementation of the NFS over RDMA right now is using the single completion queue for both sender receiver. So it might sender might block receiver, receiver might block sender. We haven't done too much research on that, but we're going to split that queue first, see whether we can boost the performance better.
Have you tried mounting a second NFS path from another NFS server on the same plane?
Right now, I only have one NFS server. So what I did, I mount multiple with no cache share, mount multi-entries on the client to the same server. Yeah, I hope.
Stuck at 2.3 gigabytes per second with multiple mounts.
Right.
If I recall correctly, the Linux NFS client shares connections when you remount.
Turn that off.
We turned that off
did?
already. Yeah.
Okay, good. That's what the no share cache mount option does.
Yeah. When they mount the entries, just using We're trying to avoid all this cache, trying to figure out where the performance bottleneck there. It's pretty encouraging, actually. I thought IPOIB should have a similar performance with RDMA based on somebody, I think somebody reported earlier, they're using large MTU size IPOIB using all the offloading features from the new HCAs. They're able to reach 3-point-some gigabytes performance per second for IPOIB. But it looks like it's a gap over there. So I hope this can encourage people to create more requirements or need to using NFS over RDMA.
Right, so that sort of gives us our encouraging story that maybe it's a good idea to move forward with this a little farther. Well, how do we go about that? I think I'll come back to this slide, actually. There are some issues about how we sort of move this code base out of the sort of unmaintained mode that it's in into a mode where we've got a shared code base that we can all work on moving forward. Upstream Linux kernel now has a lot more stringent testing requirements before they take patches. It used to be that they were happy to take contributions and get them in front of a lot of eyeballs so that they could be reviewed and tested. And basically, the Linux kernel's testing model used to be heavy beta testing. That's not true anymore. Most of the top maintainers now have complete QA set up and test plans, so they can test their subsystem very thoroughly before they ask for Linux to pull patches. So we're kind of in the same boat. If we want to start maintaining NFS over RDMA implementation in Linux as a premier capability of the client and server. So I started looking at what we would need for doing this kind of testing, and immediately saw that the test matrix would be enormous because we've got lots of HCAs. They all have somewhat different capabilities and feature sets. And we have 7 memory registration modes. The client supports 7. I think the server supports 2 or 3. And that just the test matrix becomes like a hypercube, like that drawing the NASA guy put up yesterday morning. It's sort of an 11D bristling thing. So we kind of have that kind of problem with our test matrix. And one solution to that is to retire some of the memory registration modes, at least. For example, mem windows. Every HCA that can do mem windows can do some other mode, and we don't see any real value being added by the mem windows registration modes these days. They're generally outperformed by FRMR, so why keep them around? Likewise, for bounce buffers, that was kind of a prototype. It's not used by anybody. We don't recommend it, so why keep that around? There's an all-physical mode where the client registers all physical memory on itself, so it doesn't have to do registration on the fly. It's not very secure, and it's not something we would like to encourage people to run in normal production. So that's another one that could be removed. So I've sort of been socializing this a bit to see if people really would object to this kind of simplification. So it's kind of an open question. If you guys have any comments about it, I'm very happy to hear. But it's something I think we need to do soon, because not having a testing ability to qualify incoming patches upstream is something that's kind of blocking more major work on it. Any comments here? Questions? Okay. So go back to this guy. So this is some of the things we'd like to consider in terms of improving the upper layer protocols support for NFS over RDMA. NFS v4.1 has some features that do require some support in the transport layer. We'd like to see NFS referral support RDMA transports. A referral is basically a list of server and share pairs that are alternate places where you can access the same data, usually a replica. In NFS v4.1, there's more metadata that comes with those locations. One of the pieces of metadata is a flag that says you can use RDMA on this particular location. So that would be interesting as a way for servers to advertise an RDMA capability to clients. Also, virtualization is pretty interesting. I mean, it turns out that a lot of people have been using NFS on IP over IB in guests because with SRIOV, the virtual NIC in the guest goes about as fast as bare metal. Didn't used to be the case for NFS. The virtual NICs without SRIOV are actually quite sluggish. And so NFS was almost unusable in guest environments. If NFS over RDMA is going to be a replacement for IP over IB, we need to make sure that virtualization support exists and works well. So that's definitely on the list. Anybody have other features they'd like to see? Right now, our own systems are all InfiniBand based. We know there's some qualification testing be done at Chelsea on iWarp. The only NFS server I know that's actually actively supports iWarp is the NFS server in Linux. We know that Solaris doesn't, Solaris 11 doesn't, ZFSSA doesn't currently support that. Likewise, they don't support Rocky. So we've been focusing mostly on InfiniBand, but the alternate transport fabrics are certainly on the list. And then the bottom bullet point, for those in the back who may not be able to see it, says connection and NFS server failure handling. That's one area where we've been stumbling across some issues when people do destructive testing like pulling a cable or using IB port state to shut off the InfiniBand port. We found panics and the client, the RPC over RDMA transport is not recovering robustly from these situations, and that's definitely something we want to see working well in an enterprise class NFS client implementation. So that's definitely on the list as well.
What about low memory?
The question was, what about low memory conditions? Memory allocation is going to be an issue for RPC over RDMA, but right now we think it's going to be in better shape right out of the gate than IP over IB. One of the reasons IP over IB performs so badly is because our MTU size typically is over 64 kilobytes. And what that means is for NFS large payloads like reads and writes, that data has to be copied, physically copied. And the network layer does that copy. It also has to allocate a very large buffer. Usually, since the allocations are powers of 2, to hold 64K of payload, we have to allocate a 128K buffer, which means that in low memory situations, it usually falls over. It will deadlock the whole system.
Those are physically contiguous pages, 32 physically, right? That hurts.
Yeah, that's an understatement. And it's not theoretical. We've definitely seen this in the field. So the fact that RDMA means zero copy in a lot of cases where you're talking about a huge amount of payload, that's a big win, not just for performance but also for reliability. We think that, and Linux has well-known issues with NUMA memory allocation, low memory scenarios. For example, if only one NUMA node in a system starts getting low on memory, they all act like they're getting low on memory.
For the memory, you can use in C group actually to control the resource to avoid OM killer. Yeah, that's alternative solution, but you could try.
I think I'll just finish up with this slide. One of the perennial issues with NFS, supporting NFS in the field, is being able to troubleshoot problems for customers. NFS is very, very sensitive to any kind of network problems, either connectivity burps or performance issues. And we have a sort of a toolbox that we use for diagnosing these issues. One of them is capturing wire traffic. You can use TCP dump. You can use Wireshark in IP-based deployments. Or you can add code probes. There are trace points in Linux. There's dtrace in Solaris, for example. Those are the typical ways we diagnose problems in front of customers. For NFS over RDMA, we really don't have a wire capture tool that is a complete stack. Wireshark, for example, does not support capturing IB traffic. Mellanox HCAs have this IB dump tool that actually produces a PCAP file, which is the file that contains wire trace traffic for IP, but it does not work for other fabrics like iWork. When I say analysis tools here, I mean Wireshark. That's the main analysis tool. It's got these things called dissectors, which parse the packets on the wire, and they can tease apart RPC and NFS and sort of tell you what's in each request. It's a very graphical tool, and it's quite useful. So we need a way of building out support for RDMA and InfiniBand, at least in this tool, in order for us to use a similar tool for diagnosing problems in front of customers. Another issue, a final issue here, is when we turn on debugging or capture wire traffic or put in code probes, there's usually a bandwidth problem because this stuff performs so fast and is very parallelizable. It will overrun our code probes. The code probes insert messages into a ring buffer, and that's scooped out by a user space program and put into a file. And oftentimes there's so much traffic that it overruns the ring buffer, and you of course miss the exact packet you want to see. So these are kind of the challenges that we're facing with considering deploying NFS over RDMA in front of actual real live customers. Don't have to go through that. So this is sort of my end slide. We can't do this by ourselves. We'd like to see the upstream NFS over RDMA code base supported, but we can't do this by ourselves. And so this is kind of a short list of ways that might inspire you to contribute to this project if you're interested, if you have the resources. We're very interested in continuous testing, especially by HCA vendors. We're interested in any feature requests or bug fixes you might have. We're interested in a single code base upstream, like I know that OFED has collected a bunch of patches. We're interested in seeing those moved upstream so everyone can benefit from those, and OFED doesn't have to maintain a separate set of patches anymore. We think there are a lot of important things that can be done here, and we're anxious to collaborate. Thank you.